welcome back to example 5. I didn't quite have time to finish, so I'm going to finish now and maybe give a little bit more insight on shear and moment diagrams. Alright, so when we left, we went A1, and this is kind of A1 right there. A1's right up here. It translated down when you took the area under this curve, per se, or the area in this shape, comes to here, and it is starting out where it's increasing the most because you have the most shear, and then it's still increasing, but it's increasing slightly less. When you get to this point right here, it's increasing less than it was increasing right here, but it's still increasing more. But then when you start off again, it's increasing less than it was when it stopped. So you'll actually get like that, and then it slowly goes to 0. And this is going to be your point of max moment. And as we calculated, that's 2253.1. That's this point right here, 22,753.1. Forgot 7 last time. All right. And hopefully by now you see that A3 should equal somewhere. It should equal exactly this, but given that we round a lot on moment diagrams, you're going to get to a point where it might not equal exactly. It might be a few foot-pounds away, which is no problem. You just kind of write it off and say, well, close enough. At least that's what I always did. All right, so just in your mind, we're doing this A3 right here, and it starts off where it starts off at 0. Okay, where it's not increasing at all, so it's flat. And then it goes to a point of where it's increasing the most. So it'll look something like that. And it should be around 22,750, give or take. So A3, and this should be 0. A3 equals 0.5 because it's a triangle. Obviously negative 4266.7 pounds. Times, what was that, 18 foot minus 7.33. And that will give us this distance right here. I just took the entire 18 foot minus 7.33. And that will give us what? 0.5 times 4266.7 times parentheses 18 minus 7.33. 22,762. 22,762.8 foot-pounds. And as you see, we're pretty darn close right here, within 10 foot-pounds, which is quite negligible when you're talking about 20,000 foot-pounds. So we came back to 0, and I'm fine with that. I'm saying, oh yeah, we were close enough. Because if you followed all of these 3's out, and you followed this number all the way out, and you ended up doing everything perfect, it would come out to where it works out very, very well. And it will be perfect. You will come out with 0 where you want it. But for all intents and purposes, we're good, and we just say, okay, our maximum moment is 22.5 foot kips, as I would round up to 22.5. Is that what it was? 22.8 foot kips. I'll just say 22.8 foot kips and call it good. All right, now let's work on some intuition and one moment. All right, what I'm going to do is I want to figure out other ways to find out this max positive moment. I need to erase a little bit here. But what are other ways to figure out max positive moment? Or at least to check it. And just to give a little intuition, I want to show you that the ways to find out the moment are you can cut. Remember, we can cut the section, and then we can solve using a free body diagram of the cut section. Or we can use those equations, the WL squared over 8 type equations found in some analysis books. Or we can use shear and moment diagrams. So what I want to do, just as a fun little exercise here, is to cut the section, cut the member at this point right here, the point of max moment, which is what, 7.33 foot is what we said? 7.33 foot. Now let's go ahead and see what we get. I believe it was 7.33 foot. Yes, it was. All right. Let's see what we get. So let's take another free body diagram here. There it is. And it's going to have the 400 pounds per linear foot on it. Excuse me. Let's put it over here. 400 PLF. We're going to know the reaction. 933.3 pounds. And we should have the 3,000 pounds in there. Actually, let's go from the other side. The other side, not the other side. Other side here, because it's just an easier equation. So there we go. And that's going to be what? What's 18 minus 7.33? It's a little 10.67. 4,266.7 pounds. And then we have the distributed load. And you do this the same way you do another free body diagram. And you will have your V, what I'm going to call your P, and then you have a, oh shoot, no, put the plus on there, moment. And that shows that it's plus going that way. I may be wrong. I didn't even assume anything. I just do the smiley face. I always put the P going in. I always go make the V going up, and I always make the moment doing a smiley face, which, whatever you prefer, it really doesn't matter. There may be a better way to do it, but I'm not going to go over that right now. PLF. All right. Now we want to go ahead and solve this equation right here. And there's plenty of ways you can do it. First thing I would do, you have a uniform distributed load. You make that distributed load an equivalent point load, which is 400. What do we say this is? 10.67 foot. Alright, so that'd be 400 times 10.67. 4,268. And that's pounds. Alright, we can go ahead and do the sum of the forces in the y direction equals 0. And we can also do the sum of the forces in the x direction equals 0. And that is what? P. P equals 0. Done. So this equals 0. Now we only have one unknown in the vertical direction, which is V. So we can solve for that. So V is positive. And what do we know about V, I guess? Let's stop and say, okay, what do we know about V? Well, let's look at our moment diagram, and at the point of max positive moment, what did we have for shear? We had 0. So V should be around 0. Actually, it should be perfectly 0, but given our rounding, it'll be close to, if not perfect. So let's look at V here. We say V equals, because this is actually 10.66666666 repeating, and then a 7 out there in the middle of nowhere. But let's go ahead and do this. So we'll start from, I did equal signs, minus 4,268 pounds plus 4,266.7 pounds. All right, and we end up getting V equals 4,266.7, and that's 4,268, 1.3 pounds. Which we actually know, since we did this little equation, that V equals 0. Because we of rounding. Since we rounded it, we're not going to get a perfect 0, but it should be a perfect 0. All right, so V equals 0, and we're good with that. That makes sense. That's what we wanted, because as we've said before, when V, and our shear diagram, when V equals 0, or Vx equals 0, then that's where the positive moment's going to be, and that's where we're trying to find. Alright, now let's go over to moment, and we have to sum the moments to find the max moment. And we're going to call this, let's go ahead and sum it, dang it. Let's go ahead and sum it about the cut. Let's call that point C. C for cut. About C equals 0. And at that point we have, let's call this positive. Equals M is positive. And then we're going to have a positive because it's going in this direction. 4,000. Where's 4,268, let's call it, pounds times what foot? 10.67 divided by 2. 5.34. And remember, this isn't going to come out perfect either. We're rounding numbers. It's just the nature of the beast. And then this is going to be negative moment because it's going that way. And that's, we define that as positive, so this is negative. Negative 4,266.7 pounds times 10.67. Yikes. Foot. Alright, that is our equation. Let's go ahead and solve. And as you can see, this is actually going to be double. Since this is twice this distance, and it's just relatively the same force. Force times distance equals moment, so you have twice the distance, you're going to have twice the moment. Hopefully that makes sense to you, but let's see what we get. (4268) times 5.34 equals 2279.1. And then you're subtracting 4266.7 times 10.67. It should be around 22.8, 22.7. And we end up getting, well, let's think. This was more negative, and then so this is going to be bigger, it's going to be more negative, and we flop the number over here, so it's going to be a positive moment. So our assumption was correct. Well, let's just say 35. That's foot-pounds. Alright, 22,735 foot-pounds. What do we say over here? 22,753 foot-pounds. Okay, 735, 753, potato, potato. Actually, as Megamind would say, potato, tomato, potato, tomato. Anyways, it's close enough. If you're worried about 20 foot-pounds, then we have problems. You just need to bump the thing up and call it good. So as you can see, we could cut it at that section and we still should get around the same answers. It should theoretically be the exact same, but rounding will always get you. And if you want to make some huge algebraic mess and put only variables in and then work it as one solo equation and carry all your decimals, you will get the exact same number. Alright, well I hope that was helpful and gave you a little bit more intuition. For instance, if you wanted to cut it at this point, you could find the exact same, you could find the moment at that place, and you could find the shear, and a shear should match up, and the moment should match up. You could cut it at this place, and it should do the same. You should be able to match it up. So hopefully that gives you a little bit more intuition about how shear and moment works, and how that's used to design a beam, because when you look at the beam design, you can say, oh, well, we have 0 shear at the middle, so our shear is going to have to be, let's say we put a little bit more shear reinforcing at the end. And typically you'll see that. You'll see, except for pre-stressed beams, you'll have a lot of shear reinforcings in the end, some stirrups. And then you have your max moment in the middle. And obviously this is all positive moment. So positive moment creates, you'll put more stuff down here. And typically you don't want to put, I never see anybody put stuff like this, because when you're talking about beams, they have to develop, so you're just going to go ahead and bring them all the way to the end and call it good. Alright, hope that helps. Have a good day.